In this video we will discuss the concept of electric charges. We will talk about the elementary charge, we will talk about forces between charge carriers, and also we will look at some examples of charge distributions in space. And the knowledge which you glean from this module here, from this video, forms the basis for a later understanding of the concept of the Coulomb force, which is a primary mechanism for transporting energy into electric circuits. My name is Andreas from The Fearless Engineer, and here we go. In this video we will discuss three major topics surrounding the concept of charges. The first is the elementary charge, then we take a look at forces between charges, and thirdly we will look at some examples of charge distributions in space and how they affect each other. First, let's discuss the elementary charge. Now, the amount of charge, and thus the amount of force a certain particle can exert on another particle, is measured in the unit coulombs. This is a very essential unit which you must have heard about if you go into electronics. Coulomb is the unit of charge. And a very famous physicist called Millikan, he has found in a very famous experiment that there exists a smallest amount of charge in nature below which no charge can exist. It's called the elementary charge, and it's made up of this number here, this very small number. It's 1.602 and so on and so forth times 10 to the power of minus 19 coulombs. And the interesting thing is that the electric charge of any body in nature can only be an integer multiple of the elementary charge. In order to understand this concept, you can easily imagine yourself standing on a beach and grabbing a handful of sand. And I can surely tell you that you will have grabbed an integer amount of grains in your hand. You will not be able to grab 1,000.5 grains of sand. You will either be able to grab 1,000 or 1,001 grains of sand. And it's the same with the elementary charge. And electrons, one of the basic particles which make up atoms, we have discussed this in another video, they have a charge of E-, and protons, which live in the atomic core, they have a charge of E+. So the magnitude of charge is identical, but the sign differs. And one observation which you can make is that charges of the same type, so electrons and electrons or protons and protons, they repel each other with a certain force, and charges of opposite types, they attract each other. And attraction and repulsion, and thus the charge type, they are expressed by this sign of the charge, which I have already talked about. So in the small diagram here, you can see that charges of the same type, of the same sign, they repel each other, these two here and these two here, plus and plus repels, minus and minus repels each other, while charges of opposite types, plus and minus, they attract each other. And attraction and repulsion, and thus the charge type, they are expressed by this sign here of the charge, so positive and negative. And the force effect between charge carriers, this is the fundamental mechanism for transporting energy into electrical circuits. Let's take a look at some examples here. So on the diagram below in the simulation, you can see two charges with opposing signs, a positive one on the left and a negative one on the right. And you can see a distribution of arrows pointing from positive to negative, which is called the electric field. And the force between charges is transmitted by this electric field. We will discuss this concept later when we get to the Coulomb force, but for now we have observed that there is a force acting between these two particles, and this force is transmitted by something called electric field, which is visualized here, and it's pointing from positive to negative. In a second example, we can see another electric field, now a field between two negative particles. So the sign is identical. It's both a minus sign here in these two cases. And as you can see here, in the center, in the middle between these two charges, the field gets very, very, very weak and eventually is cancelled out. And the closer we get to the charges, the stronger the field gets, but the arrows are pointing towards the charge in both cases. So you can easily imagine the force vectors acting on these individual charges, pointing away from the other charge. So the field for three charges looks a little bit different. We still have a repulsion going on between these two negative charges here. And if we start looking at the force vectors or the field vectors from the bottom moving upwards, we can see that we still have the repulsion with the vectors pointing away from the center towards the individual charges, just as with the last slide. But the further upwards we move, the stronger becomes the influence of the positive charge, and the electric field vectors emanating from the positive charge are pointing towards both negative charges here in a symmetrical fashion, because the positive charge is positioned directly in the center. And I can only encourage you to try out this link here, because you can easily make up your own field here and position charges at interesting places, also drag them around and see how the field changes, just to get an understanding, a feeling of how charges distributed in space affect each other through the concept of the electric field. And in one of the next videos we will get to a definition, an equation for the electric field, which helps us describe the strength of the electric field at an arbitrary position in space. For now, that's all. I hope you enjoyed the video. If you have any questions, please do not hesitate to drop me a question down below in the comments. I wish you a nice day. See you next time here on The Fearless Engineer.